Hi, everyone. Welcome to the John Brooks webinar, Gravity versus Low Pressure Sewers. This is the third and final installment. I can't believe it, Keith. Time has flown by. My name is Stefan Fedif. I'm a technical sales rep for the John Brooks Company. As before, the webinar will be presented by Keith McHale of Environment One, also known as E1. The presentation should run for about 45 minutes, which should allow for enough questions, enough time for questions at the end. And if you want to type in any questions during the presentation, you can do so, and we'll try and answer them as we go, or maybe we'll leave some of them to the end. And with that, I'll hand it over to Keith of Environment One. Thanks, Keith.
Thank you, Stefan. And thank you all for attending. As Stefan mentioned, this is our third part of the webinar. And just to recap, I can't make the assumption that everybody was here for part one or part two, but let's just kind of quickly go over, let me jump back a slide there. So yeah, the purpose of our webinar is to discuss sewer collection systems, gravity versus low pressure, and provide some information and some guidance on evaluating the options. So in the first two parts of the webinar series, part one and part two, we really looked at the overview of sewer systems, focusing primarily on the comparison between gravity sewer and low pressure sewer systems. In part two, we went kind of with a deeper dive on these things, looking at some of the system components, the basic design principles, as well as some of the operation and maintenance considerations that would apply to gravity sewer and that would apply to low pressure sewer system. So in the first two parts of the webinar series, the focus was more on the engineering aspects of evaluating sewer systems. Now, as part of part three, we're going to be looking at triple bottom line and life cycle cost analysis. Now, triple bottom line, which I will go into a little bit more detail as we proceed, but that's when you're looking at more than just the economic cost. You're looking at the social cost as well as the environmental. So your triple bottom line in this case is your environmental cost, your social cost, and your economic cost. The big one being the economic cost, and then we'll transition into the discussion of using a life cycle cost analysis to really evaluate the economic cost of sewer collection system options, which I think is what this slide covers. We look at the triple bottom line and the life cycle cost analysis. So just a real quick recap. We're focusing on, as we did focus on the first two parts of the webinar series, conventional gravity sewer, which consists of the service laterals, larger diameter mainline sewers, manholes, lift stations, and other appurtenances in the streets, where the sewers are designed and installed at a constant downward slope so that the wastewater is conveyed from the source to the wastewater treatment facility, primarily using gravity as the prime mover. Whereas with a pressure sewer systems, we have a grinder pump that is located on each property. So this is a pump that is located or placed in a basin, and then uses a small diameter pressure pipe buried just below the frost line. So the pump, it's a grinder pump, it macerates the solids in the wastewater, and then that allows the wastewater to be conveyed with the smaller diameter pipe. And also the prime driver here is the pumps, or rather the pumps located at each property that provide that force. So those of you that have been with us for the entire three parts, you're probably tired of seeing this slide, but it's always kind of my go-to, where I talk about the heart of the pressure sewer systems, more accurately, the hearts of a pressure sewer system. You would have this basin located at each property. Concept of pressure sewer systems was developed by Environment One about 50 years ago for the market. And as with any good product, other manufacturers have incorporated some of their products into a low pressure sewer system. So when looking at pressure sewers, there are going to be different manufacturers, but they're all going to have pretty much the same components, where you have the pump basin, and then within the pump basin, you're going to have your pumps. And those pumps could be either a progressive cavity, semi-positive displacement pump in the case of E1, or a centrifugal pump. Now, those of you who may have missed the first two parts of the webinar series, I think they are available to view that you could go back and see some of the differences and some of the advantages, disadvantages, depending on how you design a system, how you select a system, how you really move forward with the system when you're looking at the different types of pumps that are available for a pressure sewer system. So this is just kind of the quick recap part. Also within the basin, you would have your liquid level sensor, something that measures the wastewater level to turn the pump on and off, and then the pump controls and the pump removal guidance. So with the E1 progressive cavity pump, the liquid level sensors, the pump control, and the pump removal guidance are all part of the pump core. With a centrifugal pump, those might be, in most cases, are separate components that would be located within the pump basin. So we're going through the selection process, and when you're evaluating alternatives, this is not something that's unique to gravity, or I'm sorry, to wastewater collection systems, but there's always that alternative evaluation. And there's always two components of that. The objective analysis, which looks at such criteria as the performance criteria and the economic criteria. Is it a viable engineering application, and is it economically viable? Those are pretty clear-cut evaluations. But then you have the subjective analysis, and this basically comes down to what is my preference? And that preference isn't necessarily driven by someone's own core values, but just looking at some of the non-monetary criteria, such as the suitability of the wastewater collection system for the community, the ease of operation and maintenance. As part of the economic evaluation, you'll be looking at the cost of operation and maintenance, but you also want to look at the impact to the operations crew. If it's a lower cost, but is not easy for the operation and maintenance crew to address, or you need a much larger crew to handle it or staff, then that's become so subjective that you got to kind of balance that against other criteria. Is the operator familiar with it? Do they understand it? Are they willing to learn about it? And then the other components, and these two fall into the triple bottom line analysis, the community impact and the environmental impact. So as we're making this analysis, we want to look at the objective analysis, but we also need to take into consideration that subjective analysis. And that plays into the triple bottom line component. Now, many times when an engineer or municipality is doing an evaluation, they'll put up some sort of matrix and they'll give rate into different components. So here we're just looking at something where the blue horizontal bar, the smaller the bar, the less favorable the alternative is. The larger the bar, the more favorable the alternative is. So here, the top part, looking at the monetary, the subjective part, you're looking at capital cost, O&M cost. So you would go through, do an evaluation economically, assign a value to each of the systems you're looking at, in this case, gravity sewer, grinder pump sewer, step sewer, vacuum sewer. And then on the bottom part, in the bluish part of the table, you're looking at that non-monetary or subjective analysis. And again, you would go through and these components, I'm showing 1, 2, 3, 4 suitability, familiarity, ease of operation, but that list could be as long as it needs to be to do a proper evaluation. And again, that's the subjective part where you're just saying, on a scale of 1 to call it 10, is this option more suitable or less suitable? And you kind of go through that process, and then you create a scoring system that guides you through kind of the selection process. And with many things, there is a disconnect between the monetary objective analysis and the non-monetary subjective analysis. You're gonna assign different weights to different components, and you don't necessarily pick the most expensive item just because the subjective analysis becomes out a little bit favorable. But in the same sense, you also don't want to go with the cheapest alternative because some of the non-monetary subjective components might be something that is of more value. So you want something that is more favorable to your community. And part of that falls into the triple bottom line. I kind of touched on these earlier. You have 3 components of the triple bottom line. Going back not too long, whenever you look at a public infrastructure project, you would normally focus on just the capital cost or maybe the operation cost. Just looking at the economics, you want something that is economically viable. But then over the course of the years, communities have really started to put a lot more focus on some of the other components of the triple bottom line, and that is the social cost and the environmental cost. And these are costs that don't necessarily have an economic value. You can't really look at it and say, you know, one costs more than the other, but it's just a matter of how does it impact what we want to accomplish as a community? How does it disturb, you know, social costs or the community disturbance? You know, I tell this story a lot when I give presentations is, you know, my background prior to joining E1, I was a consultant engineer for 20-something years. And as a young consultant engineer, my first year or two out of college, I didn't know it, but that's when I was introduced to the concept of social cost. Because as I'm standing there overseeing the construction and watching the contractors do all the work, I'm not doing a lot. So that was a signal to the homeowners to come out and ask me, when are you going to be done? You've been tearing up the street all summer and it's a mess. I got noise, dust, mud. I had to drive all around the blocks to get around that. At the time, I did not know that was social cost, but that was when I learned it. And then we're also looking at environmental cost. So when we look at environmental cost, that's something that's kind of new, and it sometimes is a little difficult to quantify. But there's growing attention that is being paid to the impact on greenhouse gas emissions, and is leading many regulatory agencies, municipalities, and utilities to consider these environmental impacts on sewer construction. Now, I say it's kind of hard to quantify because, you know, where do you start quantifying greenhouse gas emissions? Is it only in the installation of the process? Is it in the operation of the process, the manufacture of the pump? And it's hard to very difficult to quantify some of these numbers. There are some studies out there that try to quantify the impact of greenhouse gas generation from wastewater collection, more so from wastewater treatment, but it is something that is kind of hard to quantify. Other environmental costs that we want to consider when we're looking at alternatives to a wastewater collection system is the disturbance to the wetlands and other environmentally sensitive areas, and the need to remove trees, brushes, and landscapings. So you'll recall from part 1 and part 2 of the webinar series where I discussed that one key advantage to a low pressure sewer system compared to gravity sewer system is with the low pressure sewer system, you have a small diameter pipe buried just below the frost line and does not have to go in a straight line or at a constant slope. So the pressure sewer system has the ability to deviate both horizontally and vertically. Also, it can be installed with either horizontal directional drilling methods or low impact cut and cover, where you have a much smaller backhoe, or depending on where you are and your frost line is, maybe just a trencher to install the pressure sewer system as compared to the gravity sewer system that would disturb a lot more. So if you're in an area where you have a lot of wetlands or environmentally sensitive areas, or the route is going through some areas that would have to remove trees if you had to go in a straight line, that is, if not completely negated, at least minimized when you have the pressure sewer systems, because you're not going to dig a bigger trench adjacent to the wetlands, or you can deviate, again, horizontally or vertically and go around some of these environmentally sensitive areas easier than you could with a gravity sewer system. Now, as I say, it's always hard to quantify environmental cost. There are many ways that you can look at it from, you know, sometimes you look at it cradle to grave. What does it cost? What is the greenhouse gas cost, the carbon footprint from generating the pipe, manufacture of the pipe, to retiring the system? And there's not a lot of studies on it, but when we look at environmental costs in the evaluation of sewer alternatives, one of the things to look at is the construction means and methods of pressure sewer systems compared to gravity sewer systems. As I mentioned earlier, with pressure sewer systems, you can use low impact cut and cover or trenchless technologies. So there was this report, and I don't have a date on the footnote, but I believe it was in the early 2000s. This report came out where there was an evaluation comparing the cost of trenchless versus traditional excavation methods. And this was not done for a sewer system. This was pipeline excavation in general. So gas, water, sewer, cable, anything that involved a trench. That's what they were evaluating in this process. And what they found was that construction that use trenchless technologies can result in an 80 to 97% lower greenhouse gas emissions compared to an open cut excavation. So when we look at gravity sewer versus low pressure sewer systems, it's not like low pressure sewer systems in of itself provides a more favorable environmental cost, but the means and methods in which we install that system provides a much more favorable environmental cost as it relates to the production of greenhouse gases. Additionally, you got the capital cost and the O&M cost that can be considered as part of an energy and greenhouse gas cost. As I said, there's not a lot of studies on this. I found this report some time ago. This was done in early 2000s. I believe this project was focused in Japan, and the paper was presented at WEFTEC. But what they did as part of this evaluation was look at the construction energy and the carbon emissions for different types of sewer systems. So they look at the environmental fuel consumption, the energy to produce and transport the material, the electrical consumption. Basically, as I said, or as I've already mentioned, the cradle to grave analysis. And they found that comparing gravity sewer versus pressure sewer, there's a 49% reduction in the life cycle energy of a pressure sewer system compared to the gravity sewer system. And the life cycle carbon emissions produced a 45% reduction for pressure sewers when compared to gravity sewers. So when you're looking at the environmental costs, there is the greenhouse gas emissions, the carbon emissions, the energy used to manufacture, install, and operate the system. And then again, going back, as I said, there's also the tangential environmental cost of avoiding wetlands, avoiding environmentally sensitive areas, and being able to deviate the pipeline so you don't have to take down trees or you don't have to disturb large wooded areas. So now we turn our attention over to the second component of the triple bottom line, and that is the social cost. So I kind of already covered a lot of this in my anecdote, but the social cost is that indirect construction cost associated with work that is paid for by the community. And you can see I got paid in quotations because it's not an out-of-pocket cost, but there is a cost to the community, and that cost includes business loss, diminished quality of life, the traffic disruptions, noise pollution, dust, dirt, worker safety, and damage to paved surface utilities and adjacent structures. Anyone involved in the horizontal infrastructure business, such as sewer systems, knows that sometimes it has to go over a couple construction cycles. You dig the trench, you install the pipe, you backfill the trench, you pave, and then you come back next season to address that trench again because the trench where the trench was, the pavement settled. So you do got to worry about that damage and that follow-up activities. That's what's impacting the homeowner, the businesses, the people around there. When you put in the sewer system, you're trying to solve a problem. You certainly don't want to solve a problem that creates more problems for the community. The project social cost will vary depending on location and the circumstances. It's very unique to every project. But generally, one of the things when we look at the advantages of social cost for pressure sewer system compared to gravity sewer system, a lot of it comes down to what I've already mentioned, the ability to use horizontal directional drilling or low impact cut and cover. With a pressure sewer system, you have less damage, quicker, easier restoration. There's less construction time and less disruption of that. So you're able to install more pipe, or the contractor can install more pipe per day with a low pressure sewer system than they typically can with a gravity sewer system. So you're going to have your crews and your construction equipment in the community for a shorter period of time. Potential for less impact to existing utilities. If you're in an area that has a lot of utilities, a gravity sewer system will always, or maybe I shouldn't say will always, but in most cases will be the lowest utility in a utility corridor. So if you're going into an area with existing gas mains, fiber optics, water lines, any other kind of buried utility, with the gravity sewer system, you have to work around that while also maintaining that constant slope. So there might be cases where a gravity sewer system would have to be installed at a deeper excavation just to avoid a water line or just to avoid a gas line. With the pressure sewer system, you have the ability to flexibly alter your standards horizontally and vertically. The rules of separation between utilities would still have to be followed, but you don't have to dig a deeper excavation. You just got to make sure you got that separation between water and sewer covered. provides for improved worker safety, improved vehicle and pedestrian safety, and less vibration, noise, dust, and air pollution. Another thing I learned in my early days doing construction inspection is after you went through with the gravity sewer system, there seemed to be a lot of homeowners that had cracks in their foundations, and it was caused by the project. Now, those cracks look pretty old to me, but I'm not the one who makes that determination. But it's not uncommon, and there was some, we had to do some rock blasting in eastern Massachusetts, a lot of granite, and you're blasting all day. So you're gonna have broken windows, broken or cracked foundations. With the pressure sewer systems, you're able to do that horizontal directional drilling. So here I just got a couple pictures, pictures worth 1,000 words. So this really illustrates with the gravity sewer system, this is the high social cost that is associated with that. Big equipment, deep excavations, taking out big parts of the road to install that pipe, and of course, worker safety. I did go out of my way to find pictures where most of the workers were wearing a hard hat, but it wasn't that hard for me to find pictures where you have guys in trenches without the trench box or without a hard hat or other safety mechanism. So it is important with the gravity sewer system, safety does become a very big concern.
They probably
with a low pressure, I'm sorry.
They probably just saw you with the camera and put on their helmet. Probably.
Another quick anecdote. I hope I don't run out of time telling all my stories. When I was going back to my inspection days, I used to always have to tell the contractor, can you at least have the helmet, the hard hat near you? Because this was 20 years ago when the rules weren't enforced as much. Can you at least have it near you so if someone comes by, you can pop it on your head? And that was also the time where I think we went from being construction inspectors to construction observers because we actually had no authority to make them do anything. But getting back on track now. So with the low pressure sewer system, you have a lower social cost. So you could do horizontal directional drilling. You could see some of these pictures where they are doing horizontal directional drilling or even low impact cut and cover or trenching. They're able to do it on the shoulder of the road or on the adjacent right of way out of the road. So they're not digging up the road as much. Certainly one of the advantages or one of the ways to avoid having to repave a road is never to destroy it in the first place. So these really kind of illustrate some of the key advantages that a pressure sewer system would have when we're comparing it to a gravity sewer on the social cost. And again, these are the non-monetary subjective analysis that when you're doing that evaluation, you want to look at what is the impact to the community, what is the impact to the environment, how does this impact my operators? So those are the things you want to consider. But it does come down usually at the end to the cost evaluation, the monetary valuation, looking at the capital cost as well as the operation and maintenance cost. So in that part of the sustainability, the triple bottom line, you want to make sure you capture all the costs. So you want to look at the initial capital construction cost. That's the capital construction cost for the public components, the stuff that is in the public right away, as well as the on-property components. You also may want to consider the project cost. Now, in many cases, the project cost will be the same between a gravity sewer and a pressure sewer. And project cost is a term that is open to interpretation. An engineer or municipality will define it as they see fit. But generally, the project cost includes the cost of engineering, operations, contract administration, overseeing the project. So you won't really have a lot of deviation when you're looking at that cost. And it's not uncommon because the cost will be similar to not include that when you're doing a life cycle cost analysis. Because if you're looking at two alternatives and one component is the same, there's no harm in doing or eliminating common elements. Keep it in mind that you're doing that evaluation just to compare A versus B. You're not doing that evaluation to try to really determine what is the true project cost or what is the cost of the overall project. If you really want to get a good estimate on what this infrastructure project is going to cost, you typically would want to include all the costs, including those project construction administration costs. And then the other economic costs you want to look at are the recurrent costs. These are your operation and maintenance costs as the facility operates for the next 20, 30, 40, 50 years, as well as the repair and replacement costs. So in many cases, there are going to be repairs to sewer systems. Gravity sewer systems may require lining. There will be replacement costs to lift station pumps. Grinder pumps do require maintenance. For an E1 side pod displacement pump, The pump itself has a life of about 20 years and a mean time between service of 10 years, but it is a piece of mechanical equipment. So there is a chance that it will require repair sooner than 10 years or replacement sooner than 20 years. But generally, it's a long-term investment, but you do want to make sure that you do look at those cost components. So to do that, oftentimes we'll look at a life cycle cost analysis. So the life cycle cost analysis is the economic analysis that evaluates all current and future costs necessary to construct, operate, and maintain a sewer system. So the current costs are going to be your capital expenditures, your engineering, the cost of the actual construction project itself, and then the project administration and the project cost I alluded to earlier. Then you also want to include the operation costs, typically called the OpEx. That's your operations, your maintenance, as well as your repair and replacement costs. Now, when I do life cycle cost analysis, I like to look at replacement cost as an annual cost. Instead of saying I'm going to spend X dollars in 20 years to replace a lift station, I say I'm going to spend X dollars every year, put that into a replacement fund. So when you're 20, I have the money available to do the replacement. It just makes the evaluation a little bit easier to kind of take that number, figure out the time frame in which you're going to do that replacement, as opposed to trying to guess when you might have to do that for different components. So the importance of a life cycle cost analysis is you want a structured method that provides a standardized assessment of sewer system alternatives. If you have engineers working in different offices or communities that are looking at things that have to submit information to a regulatory or a funding agency, you kind of want everything to be done in a standard method so that when someone looks at it, they know how it compares to another assessment or even the other alternative within the assessment they're currently looking at. And it provides a long-term assessment of the infrastructure project compared to only evaluating the initial project capital cost. This allows the stakeholders to really compare the alternatives on equal footing. There might be an alternative that has a lower capital construction cost now, but has a significant operation and maintenance cost. One of the traps we fell into in an industry, at least speaking from the U.S. perspective, is going back 30, 40 years when there was a lot of federal funding for projects. Municipalities were getting wastewater projects funded at 60, 70, 80% of federal money. So that made it easy for them to make the big decision. If they only got to come up with 20% of what it costs, some of them went big. And then the project gets built, the project goes into operation, and they realize nobody really put much thought into the cost associated with maintaining the system for the life of the project. So it really provides the decision makers with all the information rather needed to make that responsible decision. It's a pretty straightforward process. True for every industry, but what you want to do is take all the costs and move them into a present worth. Your life cycle cost analysis converts your current costs, which more or less are already in current dollars, any other current costs such as your contingency or your construction cost or your initial project cost. Also looks at the operation and maintenance costs and the future repair and replacement costs. So these are future costs that you want to bring back to current year dollars. The graphic on the right-hand side of this slide just shows the typical values where you're looking at the present value. You want to bring your future cost back, so you use these formulas. The second formula down is the annuity. I think if I jumped here, it's the uniform series present worth. So that takes all your future costs that occurs every year for the next N years. N is the number of periods that you're doing the evaluation. Typically, it'd be somewhere between typically between 20 and 40 years. So you want to take all of those future costs that occur in each year and bring those forward. So you just use standard economic equations. In this case, it's the uniform series present worth. We assume that the cost to maintain a pump or the cost to maintain a sewer system will be the same every year, and the discount rate adjusts for inflation. So you would bring that forward into a present year value, sum it all up into a present year value. So it's not that difficult to do. And as I say, the formulas that we have here, these are our standard economic formulas. So it's nothing really unique about doing a life cycle cost analysis for a wastewater collection system evaluation. But you want to make sure you go through and set it up properly. You want to establish the system parameters. You want to make sure you capture the initial capital construction cost, including the project cost, if that is something that you feel should be included. You also want to make sure, to the best extent possible, you capture all the operation, maintenance, repair, and replacement activities, frequency, and cost. So you really want to sit back and say, what activities have to be done, how often, and what is the unit cost of that, and what is the total cost. You also want to look at, in the case of a wastewater treatment system or wastewater collection system evaluation, is wastewater flows. With the gravity sewer system, you're going to have infiltration and inflow. You don't have infiltration and inflow with the pressure sewer system. Now that infiltration and inflow, if you recall from the first part of the webinar series, that's groundwater or rainwater that gets into the wastewater collection system. Once it's in the wastewater collection system, it has to be treated as if it were wastewater. So there's a cost associated with transporting and treating that wastewater. You have to pump it to the treatment plant, and once it gets to the treatment plant, you have to treat it. So it's important when you're doing an electrical cost evaluation, not only look at the operation and maintenance costs, but also some of the ancillary costs, such as the infiltration and inflow and the economic impact that that has on a system. And then you want to establish your financial parameters, looking at cost escalation rates, discount rates, which is the cost of money, and then the project planning period, which, as I mentioned earlier, is typically 20 to 40 years. In most cases, that's going to be dictated by the funding agency. You know, if you're funding a project on a 20-year bond, they want to make sure you do a life cycle cost analysis to show it is economically feasible for at least 20 years. So we go through, we want to do a life cycle cost analysis, and what's important, you know, this I define this as some of the keystones for a good life cycle cost analysis is you want something that is repeatable. Every time you do it, you want to have the same process. The numbers, some of the parameters will change, but you want the process to be repeatable. You also want it to be flexible. The problem with any evaluation is if it's not flexible, it may not apply, and you actually get bad information when you're trying to get a good solution. You want to be localized. You can't really look at a life cycle cost analysis that was done in one province in Canada and say, well, this is how they do it over in British Columbia, so that's how we'll do it in the Ontario area. You want to look at it from a localized standpoint. Everything is unique. You know, there's the old saying, all politics are local. I think that goes the same for all public infrastructure projects. And then you want to be defensible. So when you do a life cycle cost analysis, the one truism when you do an evaluation is someone's going to have a question. Someone's going to say, where did you come up with that number? How did you come up with that? So you want to make sure you have a system that is defensible. So we're looking at a spreadsheet-based life cycle cost analysis model. And the advantage of this is it provides consistency and ease of use. So you have, you know, as I say, one of the key keystones is repeatability. If you have the life cycle cost analysis set up as a spreadsheet-based model or any kind of model, that provides you that repeatability. It gives you that structure. It gives you the flexibility. You have a model that was set up and established, so it kind of helps in the defensibility, and also it can serve as a guidance point. So I'm going to kind of go through the discussion now on life cycle cost analysis, and I'm going to talk primarily about the economic cost, but also some of the graphics are going to show the life cycle cost analysis that E1 has developed. So this is a model, it's a Excel spreadsheet-based model that allows you to input very little information to get a quick assessment on what a wastewater collection system evaluation would be. So it's, as I said, it's a planning level tool, provides that assessment for the evaluation. Now the model we have is set up as something that's intended for comparison purposes only. It is based on standard industry practices, rough estimates, to be frank, guesses, and you know, some other assessments. So it's not something that you want to take the results and set aside as your contract budget. It's not a 100% design opinion of probable construction cost estimate. It just gives you the tool to do the evaluation. So as I go into this, I'll tell you, E1 has set up this E1 lifecycle cost model that you can download off of our website, e1.com. Right now on the website, we have the version that is imperial units developed using US-based cost. We do have one version that has metric units that we developed recently for a project in Australia. So it's in metric units, but the default cost values are in Australian dollars and Australian costs. We do have in development a Canadian version. So if anyone out there is listening, they want to get of this, you can start looking at some of the Australian version or even the US version that came off our website. But reach out to John Brooks or reach out to me, and we can kind of expedite the process of developing our Canadian model. The metric part of it is easy. The only part that hasn't really been developed is it has default costs in there. And it just takes a little bit of work to figure out what is a good default cost. So as I go through this, keep in mind you'll be looking at the screenshots of the Imperial Units US version, but soon to come Canadian version will be very similar.
Okay.
And it's what it is. It provides that quick analysis. And it does this by establishing the financial parameters. So we look at our cost escalation rate, our discount rate, and our project planning period. You put these values in there, 20 years at a real discount rate of 0.7%. As I mentioned, the optimum planning period is 20 to 40 years for a life cycle cost analysis. My personal preference is 30 years. If you're looking at 20 years or anything less than 20 years, you're not capturing all the operation and maintenance costs associated with the wastewater system. If you're looking at 40 years and certainly anything greater than 40 years, it's really hard to estimate what something is going to cost. What is the economy going to look at? What are the interest rates going to be 40 years from now? So you want someone to help you make a decision, but you don't want it to go so far out or be for too short a period that the value, the information you get in is not of any value. So the first thing you do is you kind of go through and you establish your system parameters, your initial capital construction cost. And again, this includes the engineering, project administration, oversight and commissioning as your project cost and your construction cost. And one of the things we found, we did some evaluations looking at a whole lot of gravity and a whole lot of low pressure sewer systems. And we see that the average cost savings of a low pressure sewer systems tends to be about 35–40% cheaper than a gravity sewer system. I think you might see an even greater difference in some areas in Canada, particularly as you go into some more northern areas where you would have to have a much deeper excavation, or maybe you have some very unsuitable subsurface conditions that would increase the cost of a gravity sewer system. Now, when I developed this table, it was developed from a lot of reports, and I did have some Canadian reports in there. I did not convert the dollars, but it gives you that kind of range of feel that, gravity sewer system tends to be more expensive than low pressure sewer systems. And again, I would expect to see some of those costs to be even greater when you're looking at some parts of Canada. And a lot of this is driven by just the advantages of the low pressure sewer system. Gravity sewer, you have large pipe diameters, deep excavations, large environmental disturbance. With pressure sewer system, you have a much smaller pipe diameter, leads to a shallow excavation. You can follow the contours of the land. You don't have to maintain that constant downward slope. And as I mentioned, I don't know how many times up to this point, you can use trenchless installation methods, horizontal directional drillings, or low impact cut and cover. Other cost drivers, with gravity sewage, you tend to have multiple lift stations with extensive restoration. Pressure sewer systems, it is going to depend on how big the system is, some of the topographical parameters of the system. But generally with the pressure sewer system, you're going to have few, if any, basin area lift stations. Again, going back to some of the discussion on social cost, also a big driver for economic cost. You're going to have smaller equipment, smaller crews, less environmental disturbance. You're going to get in there quicker with smaller equipment, get out of there faster. It also provides for better and more flexible construction phasing. So when you go through, you establish your additional capital construction costs. This is a screenshot from our life cycle cost model where we just have some standard parameters. So you want to look at the system components, the quantities, that gives you your total cost. And you can see on the right-hand side, the small box, you add in your contingency, those costs of what we don't know we missed, and then your project costs. So you get your total capital cost, and that is one of the key components you would do in your life cycle cost analysis. Something else to keep in mind, though, is when looking at gravity sewer versus low pressure sewer system, is not all costs are created equal. So there is a significant cost savings when you're looking at pressure sewer system compared to gravity sewer systems. But that cost savings could be even more significant. This graphic was developed looking at a series of reports, and in some cases bid tabs, where we got a breakdown from the estimated cost, and most of these were reports where the engineer did a comparison of A versus B. So we're able to get this nice breakdown where we're able to break it down between the construction costs, or the opinion of construction costs, between the mainline costs, all the appurtenances in the street, the on-property cost, the restoration cost, and the lift station cost. So we developed these graphics so you can see one of the things that really comes out of here is with the gravity sewer system, a lot of those costs are going to be done in the early stages of the project. It's all public work, with the exception of the 13% on property. That's a service lateral going up to the house. So the majority of the cost with the gravity sewer system is going to be done in the early stages of the project. With the pressure sewer system, the mainline sewer accounted for only 33% of the total cost. The appurtenances, the air release valve, any cleanup you might have, was 2% compared to 9% on gravity. And one of the big things, as I mentioned, you don't have lift stations with pressure sewer systems. So looking at this whole series and this database of reports and studies, looking at the total construction cost for a pressure sewer system, only 2% of it was attributed to lift stations, whereas 21% of the total cost for gravity sewers was attributed to lift stations. So when you're looking at that, less than half of your total construction cost for pressure sewer system is that in the public right-of-way cost that has to be extended early on. And this is where we get some of that flexibility in the construction phase, and that you could do the public work, the mainline sewer, the restoration, any appurtenances, and if you have any lifts, you can do that now and then budget for a later time, depending on how your system is structured, to the on-property components later. If you're looking at a system where you have failed gravity, if you're looking at a community where you have failed or failing septic systems, if you put in a pressure sewer system, you don't necessarily connect all those properties now. You connect them when their septic system fails. With the gravity sewer system, you're spending a lot of money now to connect people way down the road. Whereas with the pressure sewer system, you're spending less money now, and you spend the on-property component when the homeowner's septic system fails and they have to install and connect to the pressure sewer system. So that's another key advantage we look at. Then you want to look at your system parameters as they're retained to operation and maintenance. Here you got to make sure you capture all your operation and maintenance, all your equipment maintenance, your equipment repair, as well as your equipment replacement, your short-lived assets. If you have a pump that might have to be replaced, or a component that has to be replaced every 15 years or so, you want to make sure you account for that. So you want to pick up the activities and the frequency and the cost and put those into that structured methodology, such as the E1 life cycle cost model. Because it's really important to remember that a well-planned and executed proactive maintenance program is key to keeping a sewer system in good repair and operation. Maintenance is required for all wastewater collection systems. One of the things we hear a lot is that people say, well, with the gravity sewer system, I spend a lot more money up front, but I don't have to spend any operation and maintenance money. That's not true. There is regular inspection and cleaning necessary for a gravity sewer system. There's a huge industry of vac trucks, sewer lining, sewer cleaning. That's a lot of industry for something that doesn't have to be done. So that tells us that gravity sewer system is required. Now, there is no regulatory or industry standards. Often it's driven by consent or regulatory orders, but this is just kind of an idea, down in the US EPA. I've pulled this from an older report, but it's still kind of valid today. They provide some frequency, and you really want to be in there maintaining and keeping an eye on your gravity sewer system on a regular basis. And you can just kind of look at this, that if you're looking at hydro cleaning per mile, and these are some numbers that came out of that EPA report, you're looking at about something that's $2,000, $3,000 a year. And if you don't account for that in the early stages of the project, that creates a problem for you down the road. So you want to make sure as you go through the process, you capture all of the costs. That also applies to gravity sewer lift stations. Gravity sewer lift station, not only is it a big piece of mechanical equipment, but it requires daily or weekly visits, maybe quarterly mechanical and electrical detailed inspections and maintenance. Wet well has to be cleaned periodically. And then you have any power, odor control, chemicals, and landscaping. So if you're looking at a gravity sewer system as part of the evaluation, and that gravity sewer system has lift station, you want to make sure that you include the cost for that. Now, the other side of that, on the pressure sewer systems, one of the things that we also hear a lot about in our industry is people don't like pressure sewer systems because they have this fear that it's going to cost a lot to maintain. You know, we have this semi-positive displacement pump. It is only a 1 horsepower pump, so it doesn't have a lot of maintenance. But if you tell somebody that the solution to their wastewater collection needs is 200 pumps throughout the communities, they're going to say, well, I have one lift station that's already a pain. I can't imagine what it's going to be like to maintain 200. And that's really not the case, particularly with the E1 system, because this pump was developed by appliance engineers from General Electric. So they went in with this low maintenance mentality. It is a more of an appliance than is a pump. So it's a 1 horsepower semi-positive displacement pump, always operates at its best efficiency point because it has a near vertical curve. So the EPA document actually went through, and I love this quote, but it says, you know, basically, well-designed pressure sewers made easy to maintain by design have been relatively easy to maintain. So if you have a good wastewater low pressure sewer collection system with good pumps in there and a proper design, you're not going to have a lot of maintenance. Operation and maintenance of the main line is also very insignificant because you have the pumps itself that tend to flush any debris or solids that might settle in the system. So with E1, you know, if you remember back from, I think it was, I guess, part 2 of the webinar, or maybe it was part 1, but one of the first 2 parts of the webinar where I kind of did a little bit more focus on the differences between centrifugal and semi-positive displacement pump. And there is a difference. So it's important to kind of incorporate that distance, that the progressive cavity grinder pumps requires no preventative maintenance. The same can't necessarily be said for centrifugal pumps. Centrifugal pumps operate over a wide range on their pump curve, so that can create some problems. But even if you're looking at a centrifugal pump, the maintenance on it is not as bad as some people tend to fear. With the E1 system, as I mentioned earlier, there's a life expectancy of about 15 to 20 years or more. We have some pumps out there that have been in the ground for well over 20 years. And we also find through our analysis that the semi-positive displacement pump have an average mean time between service of about 10 years. It is a mechanical piece of equipment, so there can be some things that occur before 10 years. But generally, it's all in a core. It's a simple system where you have a rotor and a stator, and there are standard or almost expected service calls. You know, we know that if you start to see some changes in the pump, that it might be time to replace the rotor soon. Or if something goes wrong, generally the operations and maintenance staff will know what it is because there's not a lot of moving components. There's not a lot that can go wrong with it. So when you do have that service, it tends to be a similar component that the operation and maintenance staff will be familiar with. Cost of ownership, and this is in US dollars based on US electrical rates, but generally less than $25 per year. That's the number we use. If you really were to look at it, that number is actually probably closer to $12 per year. It's a 1 horsepower pump that operates no more than 20 minutes per day for a typical household. So it's a very low power cost. And we looked at a lot of reports and a lot of evaluations. We found that with the E1 semi-positive displacement pump, the annualized pump maintenance is about $30 to $50 per year per installed pump. Now, I do want to make a distinction that when a pump requires maintenance, it's not going to cost $30 to $50 to fix it. But if you had a collection within a community of, say, 200 pumps, and you put aside $30 to $50 per year per installed pump, when you do have that service call in year 10 for some of the pumps, you'll have that sort of, let's call it an insurance pool that you could pull from. So that's where we go to the life cycle cost evaluation. As I said, this is a tool available on E1's website. If you have trouble with that, feel free to reach out to either myself or the folks at John Brooks, and we can get you a copy through email. But it provides that evaluation of alternative sewer systems. It allows you to look at gravity sewer, low pressure sewer system, step sewer, or vacuum sewer systems. And it's a very simple process where you go in and it requires very limited information. There are 13 user entry fields. Only 2 of these fields are critical, the number of service connections and the distance between connections. Now, it goes through based on the number of service connections and the distance between connections, and it models, it makes an estimate on how much the length of pipe you're going to have for the various alternatives. Breaks down the pipe that you would have based on diameter for the low pressure sewer system. Also gives an estimate on what the components are going to cost and what the components, how what you're going to have in terms of manholes, appurtenances, and release valves. It's very flexible. I know there's at least one or two of you out there right now that are saying, yeah, and I bet you E1 comes out cheapest every time because they developed it. Now, we come out cheapest most times because it's just the intrinsic nature of low pressure sewer system. But we wanted to make sure that we eliminate any of that perceived bias. So every field in this life cycle cost model can be changed by the user. All the cost parameters, all the system components, all the default values can be changed. When you're looking at the operation and maintenance requirements, that provides flexibility as well, where the user can go in there and change all the O&M parameters and all the O&M costs that are default values within the model. So if you think that you don't really need any gravity sewer maintenance, the user can go in there and change all of those parameters to 0. So we want to make sure that we have that flexibility. So as I said, I'm not going to go into a lot on, in fact, this is kind of wrapping up. This is just kind of the introduction and tell you that it's available from our website or from John Brooks. Can get you an email copy. If you do want to learn more about this, we can set up some individual meetings, or if we get to a point where we're able to travel again throughout our territories, set up some meetings, and we have training programs on what the life cycle cost model is and how it can help you in your evaluation for sewer system alternatives. And again, as I mentioned, right now, the version that is available on our website is imperial units with the default cost being in US dollars. We have a metric version where the default costs are in Australian dollars. Either one of those could work for you at this point, because if you take the Australian version, it's in metric. All you got to do is change all the cost values to whatever you think is the appropriate value. And we do have the Canadian version in development. And if anyone really wants to get into this, let us know. And that would spur the Canadian development along a little bit better. So that's what we've got. Again, thank you all for the attendance over the course of what I call our COVID-19 webinar series. And I guess that leaves us about 10 minutes or so for questions.
Yeah, great, Keith. That's wonderful. Just a question about the cost analysis tool. Does it make a difference whether the municipality is going to take over those the systems, the pumps themselves, the pump stations, or each homeowner will own it? Is that kind of keyed into as an input here, or is it just cost and it makes no difference?
Well, I would say it's not explicitly keyed into it. We've had our distributors down in I think Texas does it a lot, where they work primarily with a lot of developers. And to be frank, the developer does not care about the operation and maintenance costs. So there, we just zero out all the O&M cost, so that the results are only in capital cost. Or if you're looking at some ways to put in loans, or you're not worried about the capital cost, you can just look at the operation and maintenance costs. So I just shot back to the screenshot that shows the result summary. And you maybe can't see it too well, but you can see where I have the graphic. It shows the construction present worth, the O&M present worth, and the base year. So the construction cost is the blue, the O&M is the green. And you can go through there and deselect those buttons so it only shows the construction or only shows the O&M. Okay,
I got you. So you can kind of separate it out.
Yeah. And like I said, with what some of our developers do is they'll go through and they'll zero out the numbers, so it doesn't even show a total O&M cost.
I found it quite enlightening that, like you said, the 35% usually, the low pressure sewer is usually in that 35% less cost overall when you look at the analysis compared to gravity. I find that interesting. You're saying, just to recap, that is mainly on the actual installation of the gravity main, or not the gravity main, I suppose, when you're in low pressure. It's all in that upfront cost of installation.
Yeah, yeah.
Okay. That's an eye opener. I know a lot of developers, obviously, they like that. You know, they don't have to put every single E1 unit in until all the houses are built. I think that that's a deferred cost, which is crucial, which obviously your calculator does kind of capture as well.
Yeah, and one of the things, going back to our developers, you know, because the model doesn't do it, but you can mess around with it. When you look at the capital construction cost, you know, this screenshot here shows the E1 system. So you can see on this example, it says there are 210, if you go down to the third from the bottom, 210 simplex grinder pump units.
Yeah.
If you're a developer and you're going to install those later, or the homeowner is going to install that when they buy the house, you can zero that number out.
Yeah. Yeah. And it's going to get phased in as the houses get sold. Yeah.
Yeah. Yeah. So definitely from a capital or a developer standpoint, they really see the cost savings in that they're not paying for that on-property component. That's something that the real estate company or the people who actually sell the houses are going to do, or the homeowner is going to do.
Sure, that makes sense. Well, it's a great tool. I've used it a couple of times, and if anyone out there does need any help, you know, we just don't want to throw it to you and have you sink or swim here. You know, we can always help you out over webinars, or we can always get Keith in to help you out. It is a good tool, and it's a good tool because it truly is unbiased. You can manipulate it and put in any numbers you really want to you know, take it away from the E1 selling product. So it is pretty cool in that way. That's a great product.
And I will say this, we've done this with a couple consultants. When you look at this, we've replaced that E1 logo with a consultant's logo or a municipality's logo. So we can work, you know, the nice thing about this model is it was developed by E1. So we can modify it. We make changes. I don't know how many special versions I have of it, where we can make it look less salesy to you. If you want to run this, you want to put it in the appendix of the evaluation, but you don't want to have a manufacturer's logo on there, we can take care of that for you.
Well, that's great.
We just want to provide the tools.
Yes, agreed, and that's what it is. It's definitely a flexible tool, and if anyone needs it, you know, get in contact with us, www.johnbrooks.ca, or give any one of your John Brooks reps a call, or e1.com. You know, we can always, E1 will definitely filter anyone from Canada to us. And I just want to thank you, Keith. This has been a really good session here. And I want to thank everyone else for attending. It's been a quick lightning session here, three sessions in this short time. But I think we've covered what we wanted to cover. And just want to thank you again for attending. And if you have any questions, you know, please visit the John Brooks website or E1. And just want you to have a safe, happy rest of the summer. Thanks a lot.
Thank you.